All right, so now we're going to take a look at one of the big branches in chemistry, which is organic chemistry. And this is important because we're going to see, and you're going to encounter lots of chemicals, lots of substances that are organic compounds. And these organic compounds will undergo different types of reactions. For example, combustion reactions, and that's something that you're going to have to address either as a firefighter or investigating fires, for example, that all start with the combustion of different types of organic compounds. Now, in order to understand their reactions, we need to take a look at what they are, what they're composed of, how we represent them, all that really important sort of foundational knowledge. So when it comes to organic chemistry, really just in a general sense, this is simply the chemistry of carbon and carbon containing compounds. Okay, that's a very, very simple definition. But as just to give you some examples of organic molecules, so things like methane. So methane has a chemical formula CH4. If you think of something that kind of sounds a little bit similar to methane, like propane, for example, that you have in your propane tanks, propane grills, this is C3H8. Maybe something like octane that you see in your fuels, that's C8. H18. If you think of things like ethanol, that's the active ingredient in um, alcoholic beverages or added to fuels, for example. So this is C2H5OH. There are many, many examples. These are just a couple that you may have come across before. So really what we're going to be focusing on here is the chemistry of carbon and carbon-containing compounds. So in order to sort of study this, now we first need to focus on carbon itself and some of the other types of atoms that we're going to see. Okay, so we're going to focus on carbon. Okay, so we're going to see mostly C's in our compounds. You're going to also see lots of hydrogen, so H's, and then we're going to see smaller amounts of oxygen. We're going to see some nitrogen, and then to a much lesser extent, we'll see things like sulfur. All right, so this really are the most common types of elements we're going to see in these organic compounds, but shaded definitely towards the carbon and the H's. So let's remember now, let's take a look at some of the properties of carbon. And what we're going to be seeing a lot of here is these elements will combine with each other via covalent bonds, right? So we talked about covalent versus ionic bonding earlier on. So these covalent bonds are where electrons are shared between your nonmetals. Okay, and these are all nonmetals that we've listed here: carbon, hydrogen, oxygen, nitrogen, sulfur. These are all nonmetals. So when they combine, they were going to share electrons via these covalent bonds. So your organic compounds then tend to be covalent compounds because they're made up of mostly nonmetals. Now, a couple things to know about the number of covalent bonds that each of these elements like to form, covalent bonds. And this is going to be a general sort of rule that we're going to follow when we look at these types of elements. So carbon likes to form 4 covalent bonds. Nitrogen likes to form 3. Oxygen, hydrogen, likes to form one covalent bond. So if you remember, so let's recall from the earlier sections on bonding, okay, we said that a covalent bond, specifically, a covalent bond represents two electrons, and we can represent that using a line, right? That single line here represents two electrons being shared. If we had a double covalent bond, then that would mean four electrons are shared. We'll see two lines. And if we had a triple covalent bond, okay, that would be six electrons shared. And that would mean we would have three of those lines. Okay, so we talked about that briefly before. We're going to see this again now, especially with carbon, right? So carbon likes to form four bonds. And if you think about now, how can it do that? Well, it can do so in all of these examples. So I can have a carbon with four single lines to it. Okay, so it's the main thing when you see your the number of bonds for carbon, for example, okay, it needs to have four lines. We can have a carbon with a double bond and two single bonds. We can have a carbon with two double bonds. We can have a carbon with a triple bond and a single bond. So in all of these cases, right, if I add together all the lines, I have four lines around the carbon, right? And this makes it very versatile. And also what this means then is that because it can participate in a variety of bonding patterns, so say versatile bonding patterns. Okay, and what this also gives it the property of is that it's very easy for carbon to connect to other carbons, either in chains of carbon or in rings or cycles. Okay, so let's take a look at an example. So if I have a carbon and another carbon, I can connect them with a single bond, and I can connect this with another carbon and another one and another one and another one, and so on and so forth. So it's very easy for it to form chains, and these can be very long, or you can think about a carbon connected to another carbon, connected to another one, and another one, and another one, and another one, and then it closes up here. This is a ring structure, and it can do this very easily as well, right? So a ring, or sometimes you refer to it as a cyclic or a cyclic structure. These two characteristics make carbon very, very, very versatile, and being able now to be found in a lot of different and especially larger types of compounds, but also small ones as well. All right, so we said that in our organic compounds, we're going to see mostly carbon. We're going to see a lot of hydrogens, and to a lesser extent, nitrogen, oxygen, and sulfur. So when you have a compound composed just of, so only of C's and H's, so carbons and hydrogens, we refer to these as hydrocarbons. Okay, so hydro from hydrogen, carbon from carbon. So hydrocarbons are made up only of C's and H's. All right. So the other thing that we didn't talk about before was that, yes, carbon likes to form four bonds. Hydrogen, on the other hand, can only form one bond because it only needs two electrons to be happy. It's an exception to the octet rule. So it can form one bond, and that's the maximum number of bonds that it likes to form. So for example, if I have a carbon with four single bonds around it, I can attach it to H's, and what I end up with is CH4. And this is a molecule called methane, and that's a fuel, as you probably know. That's a fuel that's found in your gas stove at home. It's a mixture of methane and another molecule we'll see in a second. So we've talked about structures like or formulas like this before. Right? That's all the formulas you've been using. This is a molecular formula. What we're going to see now are structures that look like these, and these are called, or formulas that look like these. These are called structural formulas. Okay, and these give us, they show how the atoms are connected. Yeah, and it gives us a lot of information, a lot of info about, in this case, our hydrocarbon. So when we have hydrocarbons made up of C's and H's, right, this is a very simple example that we talked about. This is the maybe the smallest hydrocarbon that we'll see. So this is very small, made up of just one um, carbon atom, and then we just fill in the H's. If we take a look at methane's bigger cousin, we'll see now that it looks very similar, right? So if I have two carbons like this, and I connect them with a single line, okay, so the carbons now are connected. Remember, each C needs to have four lines around it, so I'm going to give those remaining three bonds to H's, and now what I have is two C's, and if I add my H's together, I have 3 and 3, 6. This is called ethane. Okay, this is also a fuel. Okay, and I'll take this one step further. If I have three carbons, so 1, 2, 3, connected with single bonds, and then I just fill in my H's. So single lines to H's. Each carbon does have four lines around it, so the carbons are happy. H's only need one line, so they are happy as well. Now I have C3, and if I count my H's, you'll see I have 3, 4, 5, 6, 7, 8. So this then is a molecule called propane. Okay, and this is also a fuel. So in these three examples of hydrocarbons, you will see that we have methane made up of one carbon, four H's. We have ethanes, two carbons, six H's, propane, three carbons, eight H's. These all end in this A and E ending, ane, and this means they belong to a family called the alkanes. So alkanes all end in that A-N-E ending. And what defines an alkane is the fact that there are only carbon to carbon single bonds present. Okay, there aren't any carbon-carbon double bonds, for example. Alkanes are also called, so these are AKA, also known as saturated hydrocarbons. Okay, and the term saturated. So we know what hydrocarbons mean now, made up of H's and C's. Saturated means that there are as many hydrogens as the molecule can possibly accommodate. So in other words, they're saturated with hydrogens. Okay, as many H's as can be accommodated. That's what saturated hydrocarbons mean. Now, it's important to note that our treatment of organic chemistry is going to be really, really superficial. We're not going to have time to get into a lot of the nuts and bolts of this. So I'm just trying to distill down the important parts of this so that you can understand um, how we're going to apply this down the road. So we're not really going to take a whole look at shapes and all that stuff. We're just really interpreting the structures, the formulas, and then in lab you'll get a little bit of practice with this as well. All right, so organic chemistry is the study of carbon-containing compounds. They are very, very, very common. Okay, we human beings, life on the planet is actually carbon based. Okay, and that has to do with the fact that what we mentioned down here is the fact that carbon can form big chains connected to itself. It can form rings that allows larger structures to form. So larger, more complex. Right. We are complex organisms, right? We may not think of us that way, but when you compare it to things like a cell or an amoeba or these really, really tiny microorganisms, we are way more complex because we are composed of these much larger structures, and all of those are based on that carbon framework, right? The fact that carbon can form long chains or rings allows actually life to exist on the planet, which is one of the reasons why when astronomers and people involved in sort of space exploration, when they look for life on other planets, they obviously look for water because water is kind of like the solvent in which life can develop, but they also look for the presence of carbon on those planets as well, because carbon is a really good sort of framework onto which things can become more complex. So in the next few videos, we're going to take a look at are some of the other families. So under the umbrella of organic compounds, made up mostly of C's and H's, a little bit of O's, N's, and S's, and the characteristic bonding patterns. Under the umbrella of organic compounds, we've just talked about hydrocarbons, right? So made up of just C's and H's. And then under the umbrella of hydrocarbons, we have what are known as alkanes. So alkanes are saturated hydrocarbons made up of just carbon-carbon single bonds, and then the remaining bonds to the carbon are just the H's. Remember, H's just need one bond connected to them.